Hello, this is at Tektronix, and we have a presentation for you about the latest electrical standard from IEEE, the 802.3ck, which handles 100G lanes for very fast electrical interconnect of 100G, 200G, and 400G. Here is the agenda for the presentation. We are going to mostly spend some time looking at the standard. As you know, 100G per electrical lane is extremely difficult, and some of the details of the standards are interesting and important. The compliance and test solution from Tektronix will be something we will discuss in the second part, where we will explain some of the trade-offs and the decisions we made in our compliance solution for this new standard. All right, so let's look at the 100G per lane. It's in the summer of 2022 that the standard is finishing. So we have had 50G systems available roughly since 2016. That's where the 50G per lane standards finished in a similar fashion to what we are having now for the 100G. So it's about 6 years to get from 50G per lane on 26 gigabaud to 100G per lane or 53 gigabaud. It's quite a lot of effort, and it's possible that in the future this tempo will get even slower because the physics of the electrical standards are very hard. All right, so finishing 100G per lane, standard supports 100, 200, and 400. It's true that some modules support up to 8 lanes of interconnect. So theoretically, engineered system can be running as fast as 800G based on the definitions in the standard, but that would be an engineered application. The 802.3ck from IEEE only supports 100, 200, and 400. There is some benefit in considering the comparison between Ethernet and PCIe. And so let's look at the surface. So speed-wise, the standards are not far from each other. Today, PCIe ships Gen 3 or 32 giga NRZ devices. PCIe SIG is working hard on 64 giga transfer standard called Gen 6. Which actually runs also with 32 gigabaud, but unlike Gen 5, it is 32 gigabaud PAM4. So again, in PCIe lingo, that's 64 giga transfers. So you can see that both of these standards using PAM4 now, both of them are above, let's say, 30 gigabaud. And there is commonality in some of the measurement methods too. So both of them address more and more similar markets. PCIe Gen 6 is not likely to show up in any laptops near you anytime soon. And so it's mostly servers, routers, and supercomputers that use these standards. And the similarity is also forced upon the standards by the limiting opportunity for different physical design. The physics are hard and they don't leave much room for alternatives. Quickly, here is the timeline for the standard. You can see that the work started in earnest in 2018. There was several years of complete technical developments where major changes were made into yearly drafts. And over the last year or two, we have polishing the standards and fixing areas which were poorly supported or which turned out to be problematic. There were several of those. And now we are seeing that not only we have ratification at the planned end of 2022, we are also going to see in next slide that devices are appearing on the market. The standard is not developed in vacuum, and devices are available at the last stages of the standard, including silicon. So as the IEEE is ratifying the standard, the interoperability of early devices is being tested. Sometimes this is done by silicon vendors working with some of their key customers, and sometimes this is done under auspices of the Ethernet Alliance. So the Ethernet Alliance is a supporting organization supporting to Ethernet IEEE, which actually organizes an interop, and you can bring your Ethernet devices there for testing. For the first time in the April of 2022, we had 100G devices, 100G per lane devices, most of them capable of 400G on 4 lanes, but some of them just 1 lane or 2. And this interop was running for a whole week on the East Coast in the University of New Hampshire Interoperability Lab. The results of the interops are discussed under NDA with the attendees, and there will be some public summary available in July. There were some public announcement about the results already. You can Google Ethernet Alliance interop. Tektronix Pavel Živný, so that's myself. I co-chair the Ethernet Alliance physical layer part together with the IOL staff and with my co-chair from Intel. We are going through both physical layer interoperability tests, so that's compliance tests, but also interoperability of the protocol, so devices are plugged into each other, verified to support different flavors of the standard and different features. This was very productive and I think beneficial to all attendees. And we are going to have another interop in the October of 2022. So please contact Ethernet Alliance if you are interested in having your devices tested, meeting other suppliers, and see where your devices stand compared to the rest. Do note that if you want to take part, you will have to sign an NDA. The results are confidential. You will see roughly where you stand against the other companies, but you will not know exactly what company has what result, except for your own company. Overall, the results of the interop were good. The IEEE 802.3ck testing we performed passed most of the devices, and we had productive learnings about the standard, and we still brought some feedback back into the standard. And the compliance test is appearing to be a good test for the standard. So I said a lot about 100G per lane, so let's go into the details. We are talking about electrical 100G per lane. There is nothing new in 802.3ck for optics. Optical standards have been running for 100G per lane for a while, and there are other developments in the optical groups which we are not going to discuss here. So for the electricals, the 802.3ck is bringing the following. It's bringing the AUI, the CR, and KR on 1 lane. So it's the first line there on the table. Also on 2 lanes, so that's the 200G AUI, 200G base CR2, 200G base KR2, and 4-lane standards. 400G GAUI 4, 400G CR4, 400G base KR4. Yeah, I already mentioned that that's all that's in the standard. No 800G there. You could imagine that being extended. AUI has 2 flavors by itself, so I should explain a little bit the difference between AUI and the other parts. So AUI is not a standalone complete standard, it's a interconnect, attachment unit interconnect, part of the Ethernet standard. And the attachment unit could be chip to module or could be chip to chip. So C to C versus C to M. The example would be 400G AUI-4 C to M is 400G total data throughput, attachment unit interface on 4 lanes, chip to module. The additional two standards, the KR and CR, are, as you probably know, KR as a backplane and CR is a copper twin-ax cable interconnect. There is no twisted pair in 100G, and I don't know if we are going to see any twisted pair-like standards for these speeds. So overall, this supports backplanes, twin-ax cables, and interconnect connection of the modules or chip-to-chip in the AOE. Here is a slide that you might find useful or you might want to skip. So this is my interpretation or common interpretation of the lingo of the Ethernet standards alphabet soup of abbreviations. So we already said that KR is a standard for backplane, CR is for coaxial cables, and AOE is not a standard on its own right, but it's the interconnect. The definitions are somewhat not really open. For example, KR might stand for backplane because of the K in the middle, or might not. But the usage is defined simply as what IEEE says, and you could possibly find some logic in it or not. The acronyms and the numbers are changing occasionally. We had, for example, the early PAM4 standard listed as KP, but it went back to KR. The last dash digit usually specifies the number of lanes, so KR1, KR2, or AOE4 will tell you it's 1 lane or 2 lane or 4 lanes. The optical standards are listed as well here in this table. And there is also no guarantee that any of this will be staying the same it is, although it probably will. So this is Tektronix interpretation. This is not an official IEEE table, and IEEE officially says that there is no meaning behind the letters, and every acronym is simply what it is. You might feel that the namings and the plethora of speeds available at different widths might lead to confusion. That is certainly a significant problem. The interop showed us that in several cases when testing devices, we didn't have a complete understanding of what is to be tested and what modes does what device support and which of those modes need to be tested. And this will be a problem for the industry. As the success of the standard exposes more flavors of the standard, this is perhaps inevitable, but it's good to understand some of the pitfalls and be prepared. So just like in the past, we used to have problems with certain devices and certain widths and certain expectations. We are having that happening to us very much today. For example, very basic, right? What does 100G mean? So 100G device can be supported by 10 times 100G signaling, 4 times 25G signaling on NRZ both, or it can be supported by 2 times 50G signaling, that would be PAM4, or 1 times 1 lane 100G signaling. So this is all electrical examples. So if you are testing a device for 100G, do make sure that you understand which one of these it is, and if some of these devices support more than one modes, verify whether you need to test all of those modes and how to move the device from mode to mode. So this is just one example of things which can go wrong with test. Another practical concern is the device supporting AOE or CR. In a typical switch today, the front panel will have a row of cages, such as shown on the picture on the left. In his example, this is QSFP-DD format cage, 2-slot, and there is a corresponding cable on the right. Similar story for OSFP format, for example. Well, the cage typically supports, and the switch supports, either the CR, so that would be to support the cables, or the AOE standard in the same slot. So if you plug in an optical module, you are using the AUI interconnect support of the switch. If you plug in a passive copper cable, you are using the CR feature of the switch. Now, is that really obvious what is a cable and what is a module? Well, it used to be, but cables could very easily today be active optical cables. That means that they would effectively have a AUI interface, and internally they transfer or convert the electrical signaling of the AUI into an internal optical signal, which then gets transferred to the other end of the cable and presents again over there as another AUI. So cable is not necessarily just always using CR, and it's important to understand what mode is the cable using before you start testing it, and verify that besides this AUI versus CR, there is additional difference to take into account. See next slide. Let's consider this AUI test in a little bit more detail. The slides presents a AUI, then again attachment unit interface module transmitter test. So a pluggable module on the bottom left of the slide is being tested, the transmitter of the module in particular. The transmitter is broadcasting its signal into the fixtures, MCB in this case, and the signal under test is connected from TP4 into the measurement receiver, which is an oscilloscope with some particular features that's shown at the bottom right. So what could go wrong? Well, AUI is not just an AUI anymore. There is a short mode AUI and there is a long mode AUI. Let's look at that. So let's look a little bit at the short mode versus long mode of the AUI transmitter test and the AUI interface in general. The long mode versus short mode behavior of the AUI addresses the problem with the longest run of the circuit board versus the shortest run of the PCB in a system where there is a large chip in the middle of the system. Obviously, on the far side of the chip side, which is very far from the front panel, you have very much longer circuit board runs towards the panel, and the equalization you would use on the transmitters on that side would be more aggressive than on the short side, where effectively most likely the biggest problem for the designer is reflections rather than loss of these shorter runs. So for that we have two flavors of the AUI, and that's now the short mode and the long mode, and we will see if this solves the problem for different run lengths on around the big chip systems. This is roughly a subset of what would you do with let's say KR with auto negotiation, where it's quite simpler than auto negotiation, and it requires discipline of the side of the switch vendor to properly inform the switch about what runs are which, so the switch can drive the interconnect properly and also inform the AUI module about what is needed from its output transmitter. So let's consider a very common case. We are all aware, or most of us are aware, of two key module formats used for 100G signaling: the QSFP-DD and OSFP. Both of these are effectively modified older versions for lower speed signaling. We expect that when we are fixturing for test, we will select the appropriate fixture for either of those two formats. But if you are looking at a 100G signaling test, you might actually find other formats for devices. In fact, there is a whole table of them listed below the IEEE 802.3ck table, and there is a number of PMDs supportable for each connector type. So consider that before you provide yourself or provide fixtures for the test. If you find out that device under test has a different fixture, requires different fixture than what you planned, you have a significant delay before you can start testing. Besides the definitions in the standard itself, we also need to look at the way we run the compliance test and the hardware and software we need for the compliance test. The oscilloscope measurement system described by the standard is shown in the picture here, which is a cutoff from the figure 120G.7. As you can see, the oscilloscope has a reference host channel and a reference receiver, which is a part of the frequency response. And our task right now is to define what exactly is the requirement for the reference receiver. There are other requirements such as reference CRU, which we will not discuss right now. In case of the 802.3ck, the standard gives us actually two different requirements for the bandwidth of the measurement tools. So we have a reference receiver and we have the receiver noise filter. In, for example, 162.9.3, the transmitter characteristics measurements Bessel-Thomson of 40 MHz 3 dB bandwidth is described, but in 93A.1.4.1 the receiver noise filter is defined by an equation. In fact, this is a Butterworth filter. So the eye-opening measurement method, for example, uses the Butterworth filter. Both of these filters are also used other places than what I just listed here. So let's look at the reasons behind that, and also how do you actually measure this with a real oscilloscope system. In this slide, for your comparison, you can see two same bandwidth Bessel-Thomson versus Butterworth filters. Both of the filters are 40 GHz. The red filter is the traditional Bessel-Thomson fourth order filter used by many standards, both optical and electrical, in the past. You can see the roll-off is significantly slower on the Bessel-Thomson than on the blue line of the Butterworth filter. On the left you can see a response all the way to minus 40 dB. On the right is a zoom of just minus 20 dB, close to the 3 dB frequency. And so in a frequency domain, it's obvious that the Bessel-Thomson is covering somewhat higher range than what might be realistic for a practical receiver in a 802.3ck implementation. A practical oscilloscope system actually has typically a sharp frequency roll-off past the maximum oscilloscope rated bandwidth. This is particularly so in the real-time oscilloscopes. So in other words, 50 GHz oscilloscope doesn't have a large response past the 50, 52, 53, maybe 55 GHz. Following slides show a roll-off of the oscilloscope and how it interacts with requirements of the standard for, let's say, the Bessel-Thomson response. Consider the following example. The green curve, visible in the picture on the right, gives us the desired response, the Bessel-Thomson fourth order filter. The Bessel-Thomson fourth order filter is defined as a mathematical function and goes to very high or possibly infinite frequency. But obviously test and measurement equipment doesn't support such bandwidth, and even if it would not be desirable to do so. So the realistic oscilloscope, which is supposed to offer a Bessel-Thomson response, will roll off the Bessel-Thomson response at some point. The filter here is 40 GHz at every single curve, whether the ideal or the two rolled off responses. But one response on the left is rolling off around 54 GHz and another one is rolling off around 64 GHz. In this example, you can see that each of them has a different floor response, but most important is that effectively those two roll-off filters applied to the Bessel-Thomson effectively and the Bessel-Thomson response around the 54 and 64. Those are realistic responses from a normal measurement system. Based on the required bandwidth, 40 GHz in the 802.3ck for the filters, and on a roll-off which passed the 40 GHz, which will provide sufficient accuracy for measurements, we established that 50 GHz oscilloscope is somewhat insufficient or only marginally sufficient, and there is a certain amount of penalty in the results left from the roll-off of the oscilloscope just past 50 GHz. For that reason, that would be a very marginal recommendation for the measurements of the standards. On the other hand, we also considered 59 GHz roll-off for the oscilloscope, and we confirmed that it is sufficient. The results of the IEEE 802.3ck measurements are stable versus further increase past 59 GHz, and this is a good recommendation. It is therefore TEK's recommendation for oscilloscope bandwidth for the 802.3ck to get a real-time oscilloscope, or to use a real-time oscilloscope with 59 GHz bandwidth for both of the Bessel-Thomson and the Butterworth filters. No higher bandwidth is necessary. Back to the image from the standards. So the oscilloscope, the measurement receiver, and the filter, which is the reference receiver, is described in the previous slides as having sufficient bandwidth at 59 GHz. So this is our recommendation for the measurements on the CK standard, and in case of Tektronix, that oscilloscope for this would be a 59 GHz so-called SX dual stack Tektronix ATI real-time oscilloscope. Obviously, bandwidth is just one requirement on the measurement tools, and extremely low noise and several other requirements are also important. Let's consider slightly, at least on this slide, the requirements on the clock recovery. So in reality, clock recoveries could be had in two different shapes. In case of real-time oscilloscope, it's perfectly reasonable to recover the clock from captured waveform. And this is what we are actually recommending and what we are doing in the Tektronix solution for CK. The real-time oscilloscope captures a waveform, and the reference CRU is then software. Software has many advantages as a clock recovery method. It can support a very wide range of parameters, well beyond the standard. But that's not our focus here. Our focus is to support the standard. So really compliant CRU is well implemented in software and has several advantages over hardware CRUs. In particular, the software CRU exhibits perfect behavior, very tightly matching the requirement of the standard. Hardware CRUs, on the other hand, oftentimes suffer from problems. There are certain cases of jitter measurements, for example, the measurement of the EOJ, the even-odd jitter, which are stressing the performance of hardware CRU. And hardware CRUs are sometimes unable to provide clean enough trigger for some patterns. And the solution in the standard was to allow usage of shorter patterns when the hardware CRU is not performing quite as well as is necessary to pass good devices. This is not necessary in case of CRU, and for that reason we feel that the software CRU, at least as implemented in the Tektronix real-time oscilloscope solution, is really the best solution for recovering the 802.3ck standard clocks. So the advantages of capture of real-time waveform are many, and one of them is ability to, beyond just performing perfect CRU, is also capture errors and measure BER, simply because the oscilloscope record length is so long that it allows capturing enough errors in the waveform to verify or not the performance of the BER. Here is the quick summary slide for the oscilloscope solution for the transmitter test. So in the 802.3ck transmitter is obviously several possible things. It can be the host, it can be the module, and in case of active cables, it could even be the cables. And the measurements on passive cables are actually not in the scope of the oscilloscope measurements, or rather they are performed with VNA. Active cables behave effectively as an AUI interface, and they are measured the way the AUI devices such as optical modules would be measured. So this is for the transmitter test. Let's look at the receiver test. IEEE 802.3ck specifies the receiver test in the now traditional IEEE way. The receivers are stressed with a signal which is in a very controlled fashion stressful, more than let's say good transmitter signal. With such a stressed signal, the receiver then has a certain relatively higher error floor, and the receiver is tested with stress signal, reports its BER, and the BER then needs to be better than what the standard requires. So the problem for the receiver test is most of all, how do you provide exactly a setup and properly difficult stress signal for the receivers to meet. So the setup of the stress signal is significant, or the most significant part of this whole receiver test. And the standard mandates that the signal is generated in a signal generator and then calibrated with an oscilloscope. So just like for the just like for the transmitter test, we use oscilloscope, the Tektronix real-time oscilloscope DPO70K SX, when we are calibrating the signal generator. We have found that the signal generators are very critical to this task of setting up a stressed signal. In particular, the signal generator has to be very quiet, and so as not to provide more distortion or more error in the stressed signal than what the standard requires. And we have found that the Anritsu MP1900 programmable pattern generator with the particular slot driver MU196020A is the most accurate signal source with the highest signal fidelity. There are several issues besides just noise in the transmitter generator, and we found the Anritsu MP1900 to be the right tool for that. The calibration process requires then connecting, possibly through a channel, to the oscilloscope and of running some calibration tests, adjusting the generator to proper amounts of jitter, proper amount of eye closure, etc., and establishing the right signal. Let's again look to the IEEE 802.3ck document for an example of a receiver test. Here in the figure 120G9, which is the host stress input test for the CR standard, we are setting up a signal on the top left of the diagram. The pattern generator has a random jitter a sinusoidal jitter, and bounding uncorrelated jitter generator. It hides the signal under stressing the receiver. There are crosstalk signals which I will not discuss at this moment. The signal from the pattern generator on the top left of the picture is routed through the HCB, the host compliance board, into the MCB, the module compliance board. So a pair HCB MCB is used to route the signal into the oscilloscope on TP4 test point. The oscilloscope measurement is using the measurement receiver filter and the reference CRU. It recovers the signal and measures all of the parameters needed by the setup. Typically, the result of such measurement is that some parameters of the PPG have to be adjusted, some of the jitters, etc., and then verified again. After some iterations, the stress signal has the right amount of impairments, and the measurement can proceed, which in this case means that the HCB and MCB are disconnected from each other. The oscilloscope part of the setup is not used, and the HCB is now plugged into the host under test. So the signal from the pattern generator with all its impairments properly calibrated is being received by the receiver under test. The receiver under test reports its error rate, and the error rate is then evaluated whether it's passing or failing the standard. So in this fairly complex fashion, we can test the receiver for this example host of the CR compliance system. Important detail for these measurements done on the receiver is that when the setup for the PPG stress signal is measured, the oscilloscope and the HCB MCB pair, the fixture pair, has to be performing very well. Unneeded impairments in the HCB MCB pair or impairments in a low quality oscilloscope will let the user set up a not sufficiently stressful signal on their PPG. Insufficiently stressful signal will then make a receiver which should fail the test still pass, and the user will end up with receivers which are actually measuring as passing while they should be failing, and that the manufacturer will then ship invalid or failing receivers to their customers. Besides the hardware and the setups, let's also consider the software solution, the software which implements the algorithms and implements the automation necessary to test the devices efficiently. In fact, we have a combination of two packages running on the oscilloscope, and in this case, in the case of 802.3ck, we are actually always using them together. This is not two separate packages in a sense that the system includes always both packages and provides all these necessary measurements. The basic algorithmic package, the PAMJet package, is a software which has algorithms for not just 802.3ck standard, but for other standards such as PCIe and others. And the user is encouraged to use that package wherever needed for troubleshooting and use it for other things than just the 802.3ck compliance. However, although the package concludes or includes all the algorithms, there are several measurements which are in the standard which require, for example, complex looping of CTLE algorithms. This will be slow and difficult to do step by step, even with the algorithms implemented in PAMJet package. For that reason, the CK is supported by the combination of the packages, and automation is simply usable anytime some complex iterative process is needed, such as the CTLE search. And so we come to conclusion of our discussion of the IEEE 802.3ck. The standard is in the sprint to finish in 2020. We are expecting ratification in November. The silicon, the cables, the first systems are in existence in 2022 and are being demonstrated at shows, and they are also tested at the Plugfests. The Ethernet Alliance Plugfest in April 2022 tested number of devices, and we expect even more devices in October 2022. Please contact Ethernet Alliance if you are interested in taking part. Contact Tektronix for the solutions for the 802.3ck standard. Tek's real-time oscilloscope implementation supports not only this standard but also older Ethernet standards, and also supports PCIe solutions, PCIe Gen 5 and older, and the upcoming PCIe Gen 6. Thank you for attending, and good luck with your implementation of IEEE 802.3ck or other standards. Goodbye.